Physics Bites,
a science podcast in English
by the students of Notre Dame d'Ascension.
So, hello and welcome back to a new episode of Physics Bites, the English language physics podcast of the students of Notre Dame d'Ascension here in Paris. Today we have two students talking to us about exoplanets. Do you guys want to introduce yourselves?
Hi, my name is Gabriel.
So we have Gabriel, who used to be a student of mine in grade 6 and who's been doing this English class since grade 10. And
hi, I'm Josephine.
And we have Josephine, who has been a student of mine for 3 years now, physics, and in this class.
Yes.
Who is going to be speaking with a bit of difficulty today because she just had her wisdom teeth pulled out. So things might be a bit less easy than usual, but I'm sure that you guys are both going to do a really good job. So you guys talked about exoplanets.
Yes.
What are exoplanets?
So we can link this question, what are exoplanets, with are we alone in the universe? So whether or not other planets on which life could develop, if those planets exist. So first of all, what is an exoplanet? So it's a planet in another solar system.
So we're comparing that to our own planet, which is in our own solar system around the sun. And the idea being that any planet that's not in our solar system, we just call it an exoplanet.
Okay. Basically. And then to look for life, we determine what we can call the habitable zone. So the distance between the planet and its star, where water could exist at a liquid state.
So, if I remember correctly, your presentation, you kind of divided into two parts. First of all, how to observe and detect exoplanets. And then once we've talked about that, then you talked about different types of maybe exoplanets, whether it's possible to have life on there. How can we even test to identify whether life is possible or not? And then we will go into the questions from your classmates. So, Josephine, do you want to tell us about how we detect exoplanets, when the first one was, what techniques we use, is it easy, difficult, and how we overcome?
So, as you can imagine, it's quite difficult to detect exoplanets because they are very, very far away from us. But we develop different methods, so we can divide these methods into two groups. The direct method and the indirect methods. So the most used one is the transit method. So basically, it's like when you have the planet passing in front of its star, it's the brightness of the star dims a little bit.
Right.
And this dimming can be seen in light curves. And when you see that this dims is like every year or every
like a regular interval.
Like this, you can imagine that an exoplanet is passing in front of its star.
Right. So if we use a sort of analogy, it's like you're looking at a very distant light.
Yeah.
And if somebody kind of walks in front of it for a moment, the light gets a bit less bright.
Yeah.
And you're saying that planets will do this, and they will do it regularly because they're orbiting around the star.
Yes.
And so by looking at how often it happens and how it dims, we can get some information about these exoplanets.
And the orbital period of the exoplanets.
Right. So the movement around the star, their size, I guess.
Yes, their mass.
Right.
And yes, a lot of characteristics.
So let's ask the question, I think, to start with. Have we observed exoplanets?
We don't really observe exoplanets because they are like so far away from us. But I think we took some pictures, but they are not really pictures. Like we just see a small point of light.
Optically, it's very difficult to see them, but we can detect them.
Yes.
And are we very sure of there being exoplanets there, even though we can't actually see them with our own eyes. We're pretty sure that's what they are.
Yes.
Okay. Which brings us to one of the questions that, so compared to a star, a planet is very small.
Yes.
Right? So you're talking about this method of light dimming when the planet passes in front of the star. Does it dim a lot? Is it very noticeable? Do you need a very high degree of sensitivity? Like, is it a very difficult thing to observe?
I saw some of the graphics, and actually, with the methods that are used today, like NASA, we can really see that there is a dimming, a dim. And but if you want to, you can also use other methods. Like there is the direct imaging.
Right, which is actually looking at it with a telescope.
Yes.
Okay.
But it's like not really developed today. But NASA is trying to develop it more for the future, because we think that it's going to be a really good method to detect like the atmosphere and everything after. Because now we can't really determine the atmosphere of an exoplanet.
Right. If I'm not mistaken, one of the things that maybe the James Webb Space Telescope is going to do is to have means of better, I guess, studying the atmospheres of these exoplanets to get an idea of what the components are. What are the closest or the farthest exoplanets we have detected? Do you guys have any?
So for the closest exoplanet, it's called Proxima B.
Okay.
Proxima B.
Yes.
Sorry.
I think we made the link between the two.
So it orbits around Proxima Centauri,
which is the closest star to the Earth and our solar system.
which is a red dwarf star. And it's as much close as far away from us, if you want. Because even if it's the closest one to us, it's still 4.25 light years away.
Right, and I think we had one of your classmates, the group, I think it was Siddharth and Basil, who were talking about interstellar travel, which were talking to us about even if we wanted to go to this star, which is the closest star in all the universe to us, at our current speed, it would take 100,000 years approximately. So it's, like you said, it's the closest, but it's still really far. Okay, so we've detected planets around there? In the especially in the Proxima Centauri. Around Proxima Centauri star, and much more exoplanets in the. So the closest one would be this. Do you know which are the furthest exoplanets we've detected? How far away they are? How many light years?
I don't think I have this information.
Okay. But it remains within our own galaxy. We've not observed any exoplanets from another galaxy, because that would be way too far away from us, right? Already, I think the idea of using this indirect method, which is the method we've used for most of the detections, right?
Because it's the only,
It's the easiest one to use and the one we've developed the most, right? Even that is pretty difficult in a sense. It's like looking at a light a kilometer away and having it fly, go in front of it, and then you can see the light dim a tiny bit. So you have to have really good technology to do, which is why we've only been doing it recently. Okay, so what else did you guys talk about during your presentation other than this method of detection? Were there any other methods for detecting exoplanets that you guys used?
Yes, there are.
So far you've talked about the indirect method with light.
Yes.
Talked about direct observation, which is not really yet developed.
There is also the radial velocity methods. So it relies on the fact that a star does not remain stationary, and when it is orbited by a planet, so the star moves in a circle or an ellipse, and when we see this star, when it's viewed from a certain distance, this light movement affects the star's normal light spectrum or color signature, and we can use the Doppler effect to determine the mass of an exoplanet. Like we can use the transit method to determine the mass of a planet, and once we have, so with this, like when I'm not sure, but when the stars go away, the light is blue shifted,
Redshifted
and when the star
is coming towards us.
yes, it's red shifted,
Blue shifted. Yeah.
And so with this we can determine the velocity of the star.
In its rotation.
Yes.
So if I'm not mistaken, what you're saying is that when a star is it has a planet around it.
Yeah.
So it's not that the planet is turning around the star, it's that they're both turning around
yes.
like a common point, which is what we call the barycenter, right? And even if we can't see the planet, the fact that we can see the star sort of wobbling around a point, that allows us to say that, first of all, there is another mass that's turning around it,
Yes.
what that mass is, and using this information, we sort of indirectly infer that there's a planet there.
Yeah.
Okay, so it's using really just mechanics and
Yes.
the ideas of weight and rotation.
Yeah.
Okay. Is that a method that we have used to detect planets?
I think it has been used to not detect exoplanet because I think the transit method is more efficient to detect, but to establish some characteristic like the mass.
Like the mass. Okay. So once we've known that there's an exoplanet, then
yes.
we can look at this bubble,
Yeah.
and then we can say, okay, so this is the mass because that's how much it's wobbling in
exactly.
its place. Okay, that's interesting. That's using everything you guys have learned already this year in Terminal. Any other methods, maybe? No?
Not in the method, but we also talked about other things like the SETI. It's the search for extraterrestrial.
Right, SETI, the famous
yes.
program from Carl Sagan.
Exactly.
So before we get to that, Gabriel, what was the topics that you were mostly talking about during the presentation?
I was mostly talking about the history around the exoplanets, the discovery.
All right, so give us a bit of the history of it.
A bit of the history. Okay, so as I said, we have discovered the first exoplanet in 1917.
1917, 100 years ago.
Yeah,
okay.
But it was not recognized as such.
Okay.
So the first time we really thought it's an exoplanet, it was in 1992.
Okay.
So where we confirmed the detection of a exoplanet. And now
So you're saying that was in 1992 was the first time we were searching for an exoplanet and we actually were able to find one?
Yeah.
Okay.
And we were sure that it was an exoplanet.
Where was it? How far away was it? Do you know?
I don't know.
Okay.
Sorry.
Okay.
Actually, in 2022, there are more than 5,000 confirmed exoplanets,
right?
Located in more than 3,000 planetary systems.
Okay, so that was one of the questions that your classmates had for you. It was that in total, how many have we discovered? So you're saying around several thousand, 5,000 in 3,000 planetary systems. So we've found in a way that systems where there are more than one planet, we've been able to detect several planets around one single star.
And it's constantly growing.
Right. I guess as time goes on, we discover more and more quickly also. Okay. So what else did you guys talk about in your presentation? So we've talked about the methods. You sort of gave us a little history of it. And then you guys talked about, okay, what are some characteristics of some of these exoplanets, why we might be interested in it. So why would we be interested in knowing about how it is on some planet that's impossibly far away from us?
Because I think that humans are curious by nature. Like we want to discover, like, are we alone in this universe?
Sure.
And I think that NASA made kind of interview of some scientists,
right. Astronomers, astrophysicists.
Exactly. Like why are you searching for exoplanets? And they all answer that beyond the fact that yes, we are never gonna reach this planet. It's in a way like I don't know how to say it, but
try.
We we understand that we are not they say that we understand that we are not the only one in the universe,
right?
And
Although detecting exoplanets doesn't mean that they have life on them, right?
Yeah.
It's a step towards confirming or at least detecting life elsewhere, because life can't be on stars, it has to be on planets. So the fact that we have discovered planets means that, okay, maybe there's a small chance that there would be life on there. But it's a step in that direction. Okay. What do you guys think yourselves? Do you find that exciting, the idea that we've detected 5,000 planets elsewhere, some of them that might look like the Earth, even if there's no life on there? How do you guys feel about that?
I found first it's quite impressive to be able to discover those planets. But mostly I think that it could help us really change our mindset.
Okay, what do you mean?
Because we don't know if there is life in other form of life in the universe, and maybe our ego will be
we have to reevaluate our place in the universe
if we understand and discover that we are not the only form of life. I think that would be great. Yeah.
You think that it would? Okay, so we'll come back to the question of life later, but you're saying that you think that if we realize that there is life, we discovered life elsewhere, it would be good for us, not bad for us?
Yeah, clearly.
Why? Why do you think it's a good thing that we confirm that? What would be the good thing to discover that there's life elsewhere? Could it not be a danger for us? Maybe could it not mean that we're not as good as we thought or as special as we are?
No. I think it will help us improve more and more.
How so?
For me myself, I think that we are better in adversity. So maybe we could overtake the other form of life, like maybe becoming better than them.
Okay.
So maybe motivational. Yeah, to be motivational.
Okay. And Josephine, what do you think about the idea of maybe? First of all, the idea of discovering exoplanets and knowing there's so many of them and that there's going to be so many more and confirming it. How does that make you feel? And then finally, about if there's potentially life on one of these, how does that?
I think the fact that we are so tiny in the universe is for a lot of humans, it's making our ego smaller, and I think it's a good thing. Because we and I don't know, when I'm looking at the sky in the night, I can see all the stars, and I'm like, we are so small in the universe, and I feel so tiny, and I think it's a good feeling, a good sensation.
That's interesting. So instead of feeling maybe bad about being so small and insignificant, you think you feel it's a good thing.
Yes.
Okay. So let's come back to this question of exoplanets. We read this in the newspapers or in scientific journals. They're like, oh, there's this planet that kind of looks like Earth, or the atmosphere seems really good, or there is an atmosphere, or there's this temperature. How, if it's so already difficult to discover these exoplanets and that we don't actually observe them, how are we able to determine what the weather is on there, what the atmosphere is, if there is an atmosphere, if the atmosphere contains, certain gases or not? How is that? How do we do this? How is that possible?
I think they are not sure, because we don't have actually today we don't have a method which can confirm us for sure that there is this or this. But I think they can obtain the temperature of a planet from also light curves.
Right. You guys studied that last year in physics,
yes.
Right?
From light curves, and the atmosphere, I don't remember, but I think some elements of the atmosphere they can see also them. So
we did that, if you remember, in grade 10. What is the method we use to discover, for example, what is in the atmosphere of a star? How do we determine, for example, what the sun is made up of?
Light. Right.
There's a science of studying light coming from these stars. What do we call that part of physics? Do you remember? Maybe you know it in French, but not in English. So that's part of it. We call it the spectroscopy, right? We look at the spectrum of light. Remember, we had the spectra, which had little pieces of parts of the light missing, and then we know that corresponds to atoms, because atoms have their electrons that go up and down, and they absorb energy. So if we look at the spectrum of light coming from a star, we determine what that star is made up of, right? The atmosphere of the star.
But the problem is that as we can see the exoplanet,
Right.
we can have the light coming from the exoplanet.
Right, so it's very difficult because stars are big and bright, lots of light. With an exoplanet, it's not very bright and not very big, so it's all the more difficult to find this.
Yeah.
How do we determine the temperature, you said? By looking at the light curves. What do you mean by light curves?
Like they are trying to obtain temperature maps from light curves, and it's really complicated because they are trying. They haven't done it, but the goal is to represent the light curve as a mathematical model with spherical harmonics.
Oh.
And I don't really understand everything.
Well, it's pretty advanced stuff, I think, for us. Okay.
But the goal is to solve the unknown coefficients of this harmonic by fitting it with the light curve of the exoplanet. But the problem is that we don't have the light curve.
Right, so we're still not quite there. We have a method, but we have a method to analyze it, but we don't have a good method yet to have enough light to actually study it properly, you're saying. Okay. So there was one question. Is it possible for an exoplanet to be bigger than its sun? Or bigger than its star?
Yeah, I remember. So no.
In general,
no.
Is there any particular reason why it's not? I guess in a way, if the planet was bigger than the star, then the star would be orbiting the planet rather than the planet orbiting the star, right? And I think the other reason is because most of the stars in general are bigger because, let's not forget, a planet is just a mass of rock or gas, whereas a star is a flaming ball of gas with lots of energy and lots of pressure. So it's usually much, much bigger. If it was that small, it wouldn't be able to usually actually light up. It wouldn't be able to ignite, I think. Although I'm sure there are other reasons why that would not be the case. So maybe we should talk a little bit about life now that we're talking about exoplanets, extraterrestrial life, because I think there was a lot of questions that was on that, and I think it's the part of the presentation which is the one that makes people dream and fascinates them much more. So what did you guys find in general, and then we'll go into the questions.
So as I said earlier, there is the SETI, so the Search for Extraterrestrial Intelligence. So, one of the astronomers that works on this program is Frank Drake, and he established an equation, so the Drake equation.
Right.
It's not really an equation, it's rather a series of probabilities.
Right.
And it's like it takes into account the number of stars in the Milky Way, those that have planets, those that have water, those that have maybe life in it, and a lot of other things. But it's more probabilities than yes, for sure there is on this planet life and everything.
So what you're saying is he takes into he in this equation we have a whole bunch of parameters which would be necessary for life.
Yeah, to be.
And then he's saying, okay, if that's the probability for there to be this, and that's the probability for it to be this, and then you take this whole equation and you apply it to like the size of a galaxy or the size of a universe, then it tells you potentially how many
exoplanets
there might be that could have life on them, right?
Exactly.
And what number have we found? What is the number that comes out of the Drake equation of the potential number of planets that could have harbor life in them?
I don't have it, but I think a lot.
Yeah, it's more than one or two, let's say, right? Maybe a few thousand. Which begs the question: why is it that we've never seen any other intelligent life form?
Because they're also far away from us, I think. And so if we have to also if they are far away from us. If they aren't, but
so even the closest ones are pretty far away.
Yeah.
And if we look at the probability of things, the further we go away, there's more planets considered. So there's a high probability, but then they're also further away.
Yeah.
I guess there's also the idea that, for example, when you're walking in the street, you're not going to stop and like pay attention to every little ant or little creature that's there.
Yes.
You just walk by because you're so much more advanced and complex. So if we don't think of ourselves as very complex, as simple, maybe lots of extraterrestrial intelligence are so complex that for them, we're not even worth the attention in a way, right?
Exactly.
Which, is that a good thought to you, Gabriel, also? Because you guys are both into the whole, let's make our ego shrink as much as we can.
Maybe it's a bit much.
A bit too much?
Yeah.
Okay, all right. I think there was one or two questions about, are there any plans to go to any of these exoplanets? Or not even send somebody, but at least send like a probe or something to examine them? Or
we haven't sent any spacecraft directly on an exoplanet, first of all, because it's really, really far away. As we said, Proxima B is located 4.24 light years, which is over 38 trillion kilometers. And
far away.
With our current technology, it will take thousands of years to go to space. However, several proposed missions to study exoplanets have been developed. So, for example, the European Space Agency in 2029 launch the Ariel mission, and they will use a spectroscopy. So,
right,
as we said, to study the atmosphere of hundreds of exoplanets.
Okay. And this would be sort of like a space telescope that they're going to put into space?
Yeah, okay. Looks like.
Okay, so something in the same general idea as the James Webb Telescope. Did you guys come across the idea of Goldilocks planets when you guys were doing your searches for exoplanets?
No.
Goldilocks. So Goldilocks, I don't know, what do we call her in French? It's the story of this girl with blonde hair that goes into a house in the woods, and there's like, that belongs to these bears. Yeah, I think that's the Boucle d'Or. So did you guys all come across that in your studies?
No.
So what is the moral of the story of Goldilocks or Boucle d'Or? So first he goes to the one plate is too hot and the other one is too cold, and then he goes to the third one, it's just the right temperature, and then one bed is too big and then one bed is too small and the other one's just the right side. So when we talk about a Goldilocks planet, what do you think we mean by that?
Is that there is a planet with all the good characteristics
For
life.
For life, or potentially for human.
Yeah.
So a life that looks like our life, right? So you guys talked about habitable zones on a planet. What do you mean by a habitable zone?
So the habitable zone, as I said, is the distance between the planet and its star, where water could exist at a liquid state.
Yeah.
And so where life, a form of life, could develop, even though there is no definition of life accepted by everyone, and we have no precise definition of life. So,
did you guys come across anything in your research about how maybe scientists would describe life or the signs of life? Because that's a big question that we've been sort of pondering for about 50, 60 years.
Yes. I just don't remember it.
That's okay. If you remember it, it could be good. If you don't, it's not the end of the world.
I don't.
So I think we can talk about historically. For example, in the 1960s, when NASA was first going into space, they thought about the question, and they had a group of scientists sort of work together at what we call the Jet Propulsion Laboratories. One of them was James Lovelock, and the idea was that if we look at the atmosphere of the Earth and we compare it to the atmosphere of Mars or the atmosphere of Venus, Venus, very hot, very rich in like carbon dioxide, Mars, very cold. Well, their atmospheres, they look like the way they should thermodynamically speaking, based on where they are from the sun, with the amount of energy that they receive and everything. When we look at the atmosphere of the Earth and the temperature of the Earth, it doesn't look like the way it should, thermodynamically speaking. And so the idea was like, okay, well, what is it that's keeping the atmosphere of the Earth and the thermodynamics of the Earth's atmosphere sort of in a place which is not its natural equilibrium state? And their idea was like, well, that could be the sign of life, right? So if we look at a planet and we see what distance it is from its sun and what size it is and how much energy it receives, then we can use thermodynamical reasoning and equations to say, okay, it should be at this temperature, it should have this much gas of this sort and whatever. And if we observe that it's not like that, then it means that there's another force sort of working to change that thermodynamic equilibrium, and that could be a sign of life, which is one of the reasons I think we're very curious to find a way of observing the way the atmosphere of these exoplanets are and stuff like this.
Okay.
So we're nearing the end. Did you guys find anything else that was interesting that you want to share with us? Or what was your general sense of the topic? How did you find it? What did you find interesting, surprising, shocking, hard to believe? Maybe Gabriel, you want to start?
Yeah, I find it quite interesting and surprising. As I stopped studying physics.
You were a big fan of physics when you were in grade 6.
Yeah.
You were a big fan of science in general, and then...
Yeah, don't know what happened. But,
I still have the little book you gave me at the end of grade 6.
yeah, I remember. So really interesting, and I think...
I guess for you, because you don't do a lot of science in your daily classwork, it was kind of going back to the way things were a couple of years ago.
Sometimes it was a bit hard to understand certain things. But it lowered down my ego.
You're all about the ego reduction, right? Well, science is good for that. Josephine, what was the most interesting part in your research? What did you find very surprising that you didn't know?
I think that I learned a lot because I did the whole part about the methods of detection of exoplanets.
So it's one of the more technical parts of the presentation. Yeah.
But actually, when I began it, it was quite complicated. But then I realized that it was all equations that we have studied in class. The Doppler effect, Kepler's law of gravitation, and it was quite simple. And it looked really simple, but I think when they do it, it's not that simple. But and also I always love space, and I think it was really interesting to learn how we can as a human with our tiny
existence
study this whole
right. So I think that's interesting, the point that you bring up about that. So stuff that we learned in school, it seems like it has no connection to anything, but then when you can actually see an application of it, it makes it, I guess, all the more interesting to know that, okay, well, I can actually have the basic knowledge for much of really advanced research, but you're right, going from the knowledge to actually doing the application calculations, that's a long way to go, and it takes a lot of work. But that's reassuring that at least what we're doing in class isn't entirely useless, right? So I guess we can stop at that point. If you have any final remarks, no? Okay, well, thank you very much, Gabriel. Thank you very much, Josephine. I know you're in pain because of your teeth, but you did a really good job. So thank you, and thank you for listening. We have another episode coming up very soon on another exciting topic.